So this dashboard is all about folding structure of the proteins as it interacts with higher levels of increasing levels of ionic concentration or salt concentration. In this case, my reference is NaCl, so sodium chloride. And so first, what I have to decide is the range of the x-axis. Because my pH level before was like 0.5 to 12, the suggested range by ChatGPT was also 0 to 12. But I actually pressed further and asked that and clarified that what I actually wanted was a range that encompasses or that includes extreme conditions. That way we can actually see how these proteins denaturate, because much like in the temperature, if you only limit it to a certain range, then many more proteins actually do not denaturate, does not lose structure. It is only when at high levels or extremes that it loses structure, and then that's actually what is more meaningful, not to actually test a range with extreme conditions. So that's why my x-axis is 0 to 7,500. By that level, the concentration is it is already a crystal, a salt crystal, by 7,500 mm. And you can see, like, you can sort of understand like what the x values represent, what it's like, it's in the area number 1 in the first few columns. In the dashboard, you see a table there, and it also tells you the amount of salt in a liter. That's how many grams of salt per liter. Like how much, if you if it's by liter, then because mm is sort of just try to compare it to something that is understandable. So like how much that actually is weight, although it's not a weight, mm is a concentration, but kind of just gives you a rough idea of what it is, and then also give you a bit of description. So 0 is actually no salt concentration, so it's pure water, no salt. And so from there, when you keep increasing it, then we see if it's if it loses structure. So if it's a high level of base folder of the ions is actually high enough, then it may not even denature. So if it has more of the D, E, and H amino acids, and less of the K and R, because the K and R is a negative multiplier, as a destabilizer, not a stabilizer. So more of that, more of the D and E and H means it will take a while to denature, if it will denature. And K and R, kind of makes the protein sequence more vulnerable. So that's what it is. And I also have a UDF that is crafted by ChatGPT, so that we can compare if my calculation is correct. But it's actually very straightforward. It's just those amino acids. So but that's it. And then the drop rate, actually I have to make my own subjective modification with the formula, because I'm now my range is now from 0 to 7,500, and the formula that was given to me sort of makes the value immediately return 0 after 0. So kind of some modification needs to be done so that I have it as x-axis divided by 1000. So after 1000, the decay rate is accelerated. And I find that the 1000 mm, after that point, the decay rate should go faster because it's more salt concentrated. And how do I know if it's correct? I sampled some protein sequence. I created another macro that just, that I can just run once to get new proteins sequence. And then every time that happens, I would paste it in ChatGPT and ask if this is correct. If if you think that the way it denaturate, the way it interacts, the folding score as it interacts with increasing is meaningful, that it is reasonable. So I did think that, and ChatGPT also agreed that yes, 1000 mm is actually seems reasonable. Seems like seems like a good formula to apply. So that's just a multiplier. So the standard drop rate multiplied by the value in the x-axis, the current mm divided by 1000. So after 1000, it will increase more. So as you can see that before 1000 level, it's sort of the decay rate is very gradual, because it's actually, the drop rate is a fraction below 1, but after 1000 it starts increasing more, it decayed more. So I think one of my example is the brain, the CASP3, that it does not denature. And then there's an explanation to that is actually normal, but if it is abnormally activated, then it becomes a source of disease, such as Parkinson's and something like that. So you can research more on that through ChatGPT. And so what else? So the buttons of each dashboard now contains only 2 lines, because I kind of clean up the code since it's really mainly interacting with dashboard number 1. So the only thing to really do is to select to activate the dashboard. Then the macro pretty much just use the information in dashboard 1 to even make highlights to correct the table at the bottom, which sometimes loses formatting when you kind of deactivate it, because I also wanted to only activate the dashboard so that the rest of the dashboard is blank, so it's not moving, just to increase performance, which I kind of don't think really mattered that much, because it's just really, it's not memory intensive task, but I still did that, just making sure that it does not, that the constant moving does not affect the current simulation. So yeah, and also it makes the code much more cleaner. So in the next dashboards, those are just the 2 lines of codes to do. So yeah, and you might think, so where is this leading? We could also maybe later on, like I'm also learning as I go, and I just wanna, and then later on we can kind of identify from the real protein sequence, identify which you know, at the point in which it denatures, so we can make a list. So something like that can be done. So we can identify which of the full proteins does not denature at all at high concentration or at high levels of pH or even temperature, or those that do immediately. So something like that, we can get that. We can also just use the UDF. It doesn't have to be manually calculated. It's just for these dashboards, for this sort of projects, which I think is important to do a manual calculation first, or to kind of understand first how each of the environmental factors affects folding. But later on, if we want to do a compilation, then we can just use UDF, which is something I plan to do, to gather a list of which proteins denatures at this environment. So